Okay, this is about where we left off last time, right? We were saying, okay, here's a while loop. Remember, a while loop is just like an if statement, but it keeps going until that condition's not true anymore. And the while loop is your general purpose loop. It's very general. All that matters is whatever's over here is an expression that evaluates to a Boolean. You could even put a literal Boolean in here and say like, well, true, and it'll work. Now, that loop will run forever, so I mean, I don't know. Or well, false, and that loop will never run. But you still could do that. In fact, there are cases where you would say like, well, true. And then you could have like inside, there's like a keyword you could use to break out of a loop, but that's a whole other thing. While loops are your general purpose loops. But I did talk about this alternative form of a loop. It's just different syntax, okay? And it's syntax that makes a certain situation a little nicer, let's say, a little easier. Because sometimes, like, while some condition is true is very general, sometimes you have a collection of things, right? You've got a collection of information, like we were talking about strings, which is really just a collection of letters. Characters. So we have an alternative syntax for loops when you want to do something for each thing in some collection of things. So in this particular case, here is a function called vertical print for. It takes a string. It doesn't return anything. It's full of side effects. It's got a print, but whatever. It's for char in a string. A string is the variable of the thing I want to like iterate over. Iterate means like loop over. And char is just a variable name that we will use to refer to each thing at each run of the loop. So if I've got like hello for C in ASD, print C. So what is this going to do? Well, first and foremost, okay, let's just hit run. Oh, it's got to connect first. Give it a sec. There we go. Hello. Hello. Why? Well, I've got the string ASD. Can you see this reasonably well back there? Or is this significantly better? Way better? How about this? Or is that just too much? Let's go with this. So otherwise, yeah? All right. So ASD is a variable holding the string hello. I know it's a string, it's got quotes, and like we were saying, strings are interesting because it's HELLO, right? It's made up of several letters. And what's kind of funny about strings is they can be as long as we want. And it's going to work just fine. And I kind of hinted at this before too, that like that makes strings kind of peculiar because like I know how much room an integer takes up, and computers like to know how much room things take up because that's how like we divvy up like RAM. RAM is where we store stuff that our computers like using, right? So we know how much room like an integer takes up and a Boolean, but strings are funny because, well, how big is the string? Bigger strings are going to need to take up more space, right? But more on that a little later. Oops. So why does this work? Okay, ASD, string hello. For each thing in a collection of things. ASD is the collection, it's HELLO. Right? First time through the loop, we start at the beginning. Right? Where else are we going to start? Start at the beginning. So what is C going to be the first time through this loop? H. Next time through the loop, E. L. L. O. Now, why is each of these on its own line? Well, print automatically adds a new line after every time you call it. So that's why. You could, if you wanted, do this. All that matters is whatever's here is a collection of things. Now, it could be a variable like it just was, or a literal. Now, I don't do this very often, but you could, just to show you. And like I was saying before, whatever you call this doesn't matter. It's just the name of a variable. It'll work with terrible variable names. What you put here matters because, well, it needs to be containing what you want to loop over, what you want to iterate over. But this doesn't really matter. It matters to a degree that you should have a good name for it, like any other variable. C is kind of reasonable here, C for character, right? So that's reasonable in this particular case. But in general, that's the idea. So it's just a loop, but it's different syntax for the situation when you want to iterate over a collection of things. Why bother having special syntax for that? Well, iterating over a collection of things is a very common thing you're going to do. So that's why they created special syntax, just to make it a little easier. I could do the same thing with a while loop, like we have right up here. It's hardly that much different. But in this particular case, we're leveraging the indexing, if you remember, where I'm going to have a variable character index start at 0. While character index is less than the length of a string, remember we can get the length of a string. But remember, if I have a string of length n, what is the last index? It's not a trick question. Come on, you remember. n minus 1, right? Why not n? Well, because we start at 0. So if we have something of string length 5, 0, 1, 2, 3, 4. I got 5 things there, but we only go up to 4, right? So just remember that. Anyways, that's why we go up to less than the length of the string, not less than or equal to. Because if the length of the string is 10, we only want this to go from 0 to 9, right? Right? Yeah. So character index starts at 0. Well, character index is less than the length of the string. Print out a string at character index, increment. So first time through the loop, this will get the string at index 0, or the character index 0, then 1, then 2, then 3, and so on and so on and so on. It's the same as this functionally, but you can see the syntax is arguably a little simpler. If you don't like for loops, you don't have to use them ever. You could stick with while loops. It doesn't really matter. It's like a more general type of a loop, but for loops are kind of handy. So any questions about that? Now, for those of you, I think I mentioned this last time, for those of you with experience in other programming languages like C or C++ or Java or something, you will have seen for loops before, but they're not the same as this, okay? This is more of an enhanced for loop, like a for each loop that you might be familiar with in those languages that you may or may not actually have seen. So don't think this is like your regular counting for loop. We can use it like a counting for loop pretty easily, but it really isn't the same thing. But that's kind of like getting into like technicalities that may or may not matter to you. But let's carry on. All right, so vertical print 4. Yeah, it doesn't really matter. Okay, immutability. This is where we left off last time. Mutability means we can go and change something about it. Okay? Immutability means you can't. Once it's set, it's stuck. You can't change it. Right now, chances are you're thinking to yourself, well, I like mutability. I want to be able to change things whenever I want, right? Immutability sounds like it's going to be more difficult to deal with. You're wrong. We love immutability. It creates, if you follow a design where you treat everything and, if possible, make everything immutable, you're going to have way fewer issues and headaches as you go. So this is an example of, like, if you make things mutable, you're going to trade like convenience, like short-term convenience for long-term giant headaches that you'll never dig yourself out of. So FYI. I'm just warning you. And mutable, so if it's mutable, you can mutate it. You can change it, okay? Yeah, so what do I mean by that? Well, if I have the string, if I could say like equals ASD at index 1, for example, print letter, there we go. Great, right? Nothing crazy. What did I do? I've got the string hello. I said, give me the letter at index 1, which is, remember, not H. What index is H at? 0. 1 is the E. Put E into the variable letter, print out letter, we see E. Okay? So if we can get information out of the string, Now, okay, pause on that thought. Let's go here, right? If I say like A equals 5, print A. A equals A minus 2, print A. Like I can go and like change what's in A, no problem, right? I can also go like B equals hello, and then, oops. What's going on? B equals not hello. I can change like what B is, right? But here's what I can't do. I can't do the opposite of this. So if I can get something, can I turn this into like that, right? So the idea is go to the string at index 1 and turn it into an x. So replace the e with an x. That's what the motivation of code like this would be. But it won't work. String object does not support item assignment. It's immutable. You can't go and change the string. Now, if you're looking at this and being like, but you just changed the string. Not quite. Let me draw for you what's happening. Strings will act differently than the other types we've seen before. Things like integers and booleans and floats act a little bit differently than strings. We use the word like primitive type to kind of like refer to those things, but integers are great because they fit nicely into a chunk, okay, of RAM. So if I've got RAM, think of RAM as like a giant list, right? I can put the integer like 17 in there and the computer's happy, okay? Great. And this is traditionally speaking. Python does some funny things to like make it better, but traditionally speaking. We have the integer 17, it fits nicely in there. But if I have the string hello, it's going to have to work like HELLO or something, right? Like it's going to actually take up more. So I'm going to visualize this a little bit. And I'm going to go into far more detail of how this works at a high level in like the next topic. I believe it's the next topic. But I'm still going to give you the idea right now. Here, right there, where I say B, here's B, and here's its little box that references, that's like its variable, what it stores. If I have the number 17 in there, that's what I have, okay? But when I have something like a string, really what I'll have is over here, I'll have the string hello. That's stored somewhere. But what's really in here is a reference to that string, okay? Now, what's going on? Again, more detail on this in like the next topic. Maybe it's not the immediate next, but the next, but very soon. So this is B. It's got a reference to that hello. But down here, what I'm doing is I'm saying, no. Okay, no, not hello. And I'm replacing this with this, okay? So what's stored in B can change in the same way that it does for an integer. But this thing itself can't change. So let me draw that again, going back to this. Why does this not work? So what this is saying, it all comes down to what the code says. What this is saying is, let's say this is ASD now. Go to ASD at index 1, that's this right here, and try to change that to an X. So try to go into the string and change it. It won't let me because the string is immutable. That's the nuanced difference. Is here, why could I change it? Because I was changing what was here. Why could I not change it here? Because I was trying to go in and actually mutate the actual string itself. That's the key difference. This will probably or hopefully get a lot more clear in a topic or so. But that's just the idea at this stage. That's why it's mad and it's not letting us. And there is a difference. Any questions about this idea, though? I'll be surprised if there's no questions, or you all understand it completely and it makes perfect sense. That's wonderful. All right. So yeah, it won't work. Now, if you say, but I really want to change that string, you can't. But I really want to, you can't. But I really, really want to. Okay, here's what you can do. What you do is you take the old string, make a copy of it when making the new one. So what this is saying here is A string is hello world, and this says go to A string. Here, let's just copy it and so I can run it. And then, okay, print. Well, here, let's change this to like an X to make it more obvious. There. So what did I do? I got the word hello. That's A string from 0 to 5, 0, 1, 2, 3, 4. Then concatenate it with the string X. Then concatenate that with the string from this one from index 6, I guess here, 6, all the way to the end. So I'm taking parts of the old one to make a new one with the change I want. I did not change this, though. I made a new string with the changes I wanted. Huge difference. And don't let it confuse you. Like if I do this and get rid of the whole reference to B string, it's going to work. And you're like, hell, well, you changed it. Well, no, I made a new one and then updated what A string was referencing. Just slow down. What does the code say? But again, more on this a little later. Well, I'll explain a little bit more why it does it like this. And then when you know the why, I suspect you'll be able to follow it along a lot easier. All right. So, linear search. Linear search is probably if I were to say like, okay, what's like the biggest, like most important algorithm you learn in 161? It's linear search, okay? Linear search, this is the big one. You already did a linear search on assignment 1. A linear search, all it means is go through each thing and check something about it. Well, you did in assignment 1, which, by the way, who saw the for loop in assignment 1? Good. You go through each thing, and in this case, what were we checking? For each thing, does it fall within some box, right? And then if it did, you counted it, otherwise you didn't. That's what you were doing. We are going to see a lot of variations of linear searches. Here is the most basic form of a linear search. And we'll do this one together, okay? Here's the problem. I want to see if a given letter exists within a string, okay? So make a function called character is in, and then I'm calling it needle haystack, right? Needle's the thing I'm looking for, haystack is the thing I'm going to search through, right? So is the letter A in the string hello, for example? That would be false. Is E in hello? True. Okay? Actually, I lied. I want to give you a chance to try this. You're going to want to do something like with a for loop. Okay? Like this. And you're probably going to want a condition in there. But I'll give you a few minutes to try this one on your own. And if you think you got it right, you can confirm it by copying and pasting these assert tests. And if you can run it and they all pass, well done. So take a few minutes and get this one working. if you're stuck, and I realize what I'm going to say might sound obvious, but it might surprise you how it's not obvious. If you're stuck, think about how you would do it. If you had like a pile of papers and you were looking for a paper with your name on it, how would you search through it to confirm if the thing is there or not? And that's your algorithm. You're not that special. How you would do it is the same way the computer would probably want to do it. Bless you. Raise your hand if you're done. Okay. I'm still going to give you a few minutes. Don't worry. Don't worry. It's a tricky one. This is the first, like everything we've written so far has been an algorithm, obviously. This is like what I would say is your first big, real general purpose algorithm. The number of linear searches I've written in my life is, I have no idea. A bajillion, I don't know. Very common general purpose algorithm. Okay, let's take a moment. Everyone look up here again. So let's think about how we would do this as a human. So I've gotten this far, right? So I've defined, okay, I've got the signature of the function, great. Now okay, so for each character in Haystack, for each thing in the collection of things, imagine I gave to you a long string. Okay, you can only look at one letter at a time. And I'm asking you, does this long string contain the letter C? What do? Well, you start by looking at the first letter, right? And say, is this C? If it is, maybe I shouldn't say C. Let's say X. I don't know. I'm looking for X. If the first thing I look at is X, what can I conclude? It's not a trick question. It's a stupid question you all should be able to answer pretty easily. If I'm looking for the letter X, and the first thing I look for is the letter X, what can I conclude? It's true. I found, X is in this string. Great. If it's not, what can I conclude? False. Well, maybe. I don't know. Can I conclude if X is in this long string or not by looking at the first letter? No. So if I see an X, I can conclude it's there. If I don't see an X, what can I conclude? I got to keep looking. So I go to the next letter. Is that an X? If it is, awesome. If it's not, keep looking. When can I finally conclude that X is not there if it's not there? If I've looked at every single letter along the way and none of them are X, if I ever get to the end of that string and it's not there, it's not there. Let's come up with a different version, right? Maybe that's still like a little abstract. Sure, we're talking about strings, but if I gave you a pile of exams and said, find your exam in there, okay? What are you going to do? You're going to look at is this mine? No. Is this mine? No. Is this mine? No. Like that's what you do, right? So that's the algorithm. And you can only conclude your exam is not there if you look at every one and go, mine wasn't in here. It's the only way. So that's the algorithm. How you would do it is the same way we want to tell the computer to do it. So if you haven't got, like I'll give you a few more minutes to try to figure this one out because this is an important one. I want to give you a good try, a good chance to try to figure this one out. If you don't, you're normal. Although it is a simple algorithm, it is not trivial. Big difference. Did you get it? Well, not a bad try, not a bad strategy. Okay, I added a line. If C, the current character, is equal to needle, the thing I'm looking for, what can I conclude? Again, not a trick question, a really simple question that you should be able to answer. What can I conclude? If C is the thing I'm looking for, if the current character is the thing I'm looking for, what do I know? It's there. I can return true. Whoop. Right. Who has this? Otherwise, return false. Right? Makes sense, right? And if we run it, it fails. Actually, it fails at that one, which is interesting. Oh, right, because it doesn't return anything. Who here has this? And who here is wondering why it doesn't work? Here's why. What does the code say? Let's look at this. Let's say I'm looking for A and hello, for example. Okay? I ask the question, okay, is C, which is H, is H equal to A? Is it? False. So I don't do this. I go here. Oh, I return false. Done. Remember, whenever your functions hit a return, it stops. All you're doing with the way you've written it here is checking the first character only. If the first character is the thing I'm looking for, it's there. If it's not the first, like if it's not though, oh, then it must not be in there. Imagine taking a stack of exams, and by the way, I'm saying this to be like, to have some fun. But obviously you know that if I gave you a stack of exams and said, oh, find your paper in there, and you only looked at the first one and be like, this one's not mine, it must not be in here. Obviously, that's ridiculous. But that's what that code means. And if you did that, that's fine. This is probably the most common mistake that you will ever see at this stage. So how do we change this? It's shockingly simple. Oops. There. Oh, character is in is not defined. What are you talking about?
The function name is different from the assertion call.
That'll do it. There you go. Sir, there we go. So, what does this mean? If C is the thing I'm looking for, return true. As soon as I find the thing I'm looking for, I know it's there. If I don't find it, I got to keep looking. Only when this loop finishes running, because this loop will look at every single character in the string, and it finishes, this line here, line 5, will only ever run after we've looked at every single thing in that string. Meaning, if we ever get here and we never return true, if we ever finish this loop having never returned true, that means it's not there. And if you're struggling with what that means, what? Slow down. It's the same algorithm that I know you have all executed before, perfectly fine, but it was you as a human, not code. Look at each thing. As soon as I find it, I stop looking, I found it. We can return true. But if I ever finish looking at every single exam in that pile and I don't find what I'm looking for, I'm done looking at everything, return false. It's not there. Questions about this? I'm expecting questions, so ask now. Remember, if you have a question, chances are half the room has the same question, so do everyone a favor and just ask the question. Yes?
When I did this one for my first try, I put in if needle equals haystack at hay.
At head?
At hay, or at, for this one it would be if needle equals haystack at C.
If needle, like you just mean like this?
Haystack, if it was,
Like at index.
yeah, at index.
Well, did you use a while loop?
No.
Like needle at C like this?
No.
Well, okay. Let me have a quick look.
I figured it out.
But what did you, but it didn't work.
I originally did that.
At hay. Well, what's hay? For hay and haystack. Well, okay. So,
Why?
yeah. Here's why that won't work. Is because, whoop. This would be the equivalent, right?
Yeah.
You called it hay, right? So why won't this work? C is going to be a character, right? Not an integer. You can index strings with integers, not characters. Now, I know what you're thinking. If this was a while loop and we were using a counter, this would be the way to do it. In fact, as a quick exercise, let's change it to a version where that would work. I'm going to get rid of this, and I'm going to say, or let's call it, go away, index 0. Well, index is less than the length of haystack if needle equals haystack at index. Oops, I'm in an infinite loop. What did I forget to do so foolishly? There. Much better. And they all pass. I accidentally made an infinite loop. I just kept looking at index 0 forever, right? Because I never incremented the index. The loop would never have ended. So this is how we could make it work, is if index is like an integer, and then we can index the string as an integer. It's functionally equivalent. Different syntax, different code, but it means the same thing. In fact, this is maybe I should take a moment to say, like, look, see this code? Like, look at that code, okay? And if I go back to the version with the for loop, here, actually, let me just do this. Do we agree that this code and this code is different? Right? It's the exact, in spite of the code being different, it's the exact same algorithm. The algorithm are like the steps, okay? It's the like, what is the computation taking place, right? The syntax and the algorithm are obviously related, but the syntax is not the algorithm. What does this say? Well, what does it mean? The syntax is, okay, well, it's less than the length. Is it true? Okay, increment, right? That's what the syntax is saying. But what does this mean? Look at each thing. If it's the thing I'm looking for, return true. If not, keep looking at the next thing, and if I ever finish, return false. Here, keep looking at each thing. If it's what I'm looking for, I found it. If not, keep looking, and if I ever finish, return false. It's the same algorithm. The code is different, the syntax is different, but what it means, the semantics, the same. Interesting, right? Other questions about what we just observed? Yeah? No? Or just a scratch? Just a scratch. Okay. I got excited. Other questions? Anybody? All right. So there we go. Linear search. Oh, and then here's an example. Here's the broken one. Why does this not work? Well, I'm doing it with a while loop, but it's also that if I find it, return true, otherwise return false. Why is this not right? We already just kind of discussed it, right? This would only ever look at the first thing. If the thing at 0 is what I'm looking for, return true, otherwise return false. And remember, as soon as your function hits a return, it stops executing. It's done. All right, yeah, okay. I kind of already explained this, but I'm going to just say it again just in case. So generalized beyond strings, we could do a linear search on many things. For example, a stack of exams, a lineup of people. It's important to note that we can confirm that a given thing exists in the collection as soon as we find it, but we can't conclude anything about whether it does not exist until we've exhausted the whole collection. That's the big thing. So for example, consider looking for X in the sequence of unknown elements. This is my unknown elements. The computer, although when we look at the screen, we could see all those numbers, but the computer could still only analyze like one number at a time. So I'm going to represent this collection of things as question marks, because I don't really know what's there until I look at it. If the thing I'm looking for, I look at the first thing, is that what I'm looking for? If it's not, I got to keep looking, right? That stack of exams, I don't know what's on them until I look at them. Yeah, so if I had a length 10 sequence, okay, so here's the thing. Here's some what's the word I want to use? In the best, okay, how can I word this? Here is some, remember how I talked a little bit in the past about what makes an algorithm good or bad or whatnot, right? And we never really touched on that. We will touch on that a little bit, but this is a little bit of a taste of that. If I gave you a list of 10 elements, how many things must you look at to guarantee that something is not there? There's 10 things. Come on. 10. What about 20? 100. Notice What about n? N. Notice that as the size of the thing, as the size of the list grows, the amount of things you have to look at, the amount of work you have to do, grows the same way. That's a fancy way of saying, look, if I doubled the number of things to look at, it's going to take you twice as long. Right? Makes sense. But it turns out there's a lot of algorithms out there where, like, if you double the input size, it'll take 4 times as long. Or way worse, or maybe a little better. But we'll talk a little bit about that later. So that's like the worst case scenario, though. What about the best case scenario? How many things, in the best case scenario, how many things do I have to look at to tell you if the thing exists in there or not? 1. Does it matter how big it is? No. Yeah. But that's, I mean, if we get lucky, right? That's kind of interesting. Okay, oh yeah, well. All right, so I kind of like did this one already. What if I said, don't tell me whether it exists or not? What if your job was to tell me the index in which it exists? And let's say if there's multiple versions of like multiple copies of that letter, just tell me the first one, right? So how can I do that? Well, that one's going to be hard to do with a for loop. We can do it with the for loop, we just have to add some extra stuff to it. It's pretty easy to do with a while loop. Return, well, we should fix this to be like int. Instead of returning true, what should I return? If I find it at index, which index is it at? In index. If it's the first time, it's 0. If it's the next time, it's 1, and so on. So the value of index, which is where I find it, will be where it is. And then, well, actually, here's a funny question. What should you return? If I'm returning the index of the first occurrence, what should I return if there's nothing in there? Well, not nothing in there. What should I return if I don't find it? Let me make sure this question is clear, because this is a fun one. The job is, tell me the index of the first occurrence of needle in haystack. If it exists, if it doesn't exist, I should return what? What ideas you got? None? That's workable. Now, some could argue, well, that's not the best because like it's mixing types. None is its own type. I'm expecting an integer to come back. So what happens if I, none? Not bad, but we could do something similar that maybe is better. What else? Any other ideas? No? 0? Well, but what happens if we find something at index 0? Right? So if the thing exists at index 0, -1. -1 is a common example of what we would say is a sentinel value. That's just a fancy way of saying, like, look. It's going to tell you the index of where it exists, right? But the index -1 isn't a thing. I know it kind of is in Python because of the syntactic sugar about how -1 means like length -1, but that's not really an index, right? So -1 has super special meaning that if I ever get -1 back, I know it's not there, okay? So -1 is commonly what we call a sentinel value. Now, when she said none is effectively a sentinel value as well. So there's actually nothing wrong with using none. Maybe it's a good idea. But if you're really like uptight about your types, you like -1, well, it's still an integer, but it can't possibly be right. So there you go. Sometimes too, what people will do is like are not found. There. Right, what do I return? Not found. Well, what's not? Well, it's -1, but if, now it's pretty obvious. It's some special value that means not found, right? Now, typically an experienced programmer in this context would see -1 and be like, it's a sentinel value. But there's nothing wrong with making your code more readable. But anyways. Other questions about any of that? All right. String trivia. Now I'm just going to blitz some string trivia to you. You can create strings with single quotes or double quotes. I recommend using double quotes because it's more standard across multiple different languages and you get a little bit more flexibility with double quotes. But if you really wanted, you could use single quotes. You can concatenate strings. Plus on strings, when you add strings together, it means concatenate. You can multiply strings with a number, which is interesting, but it just means concatenate it with itself that many times. You can get the type of a string, right? The type of a string is a string. A string can exist that contains nothing, though, which is interesting. So this is an empty string. Its length is 0, but it's a string, which is kind of neat. There's importance there. It exists, it's just there's nothing in it, right? Sometimes, like what if like you had like a long string and you wanted it to like print on multiple lines though? How can you make that happen? /n, right? Like here's what I mean, right? Like imagine down here I've got the string like if I want to do this, right? But that ain't going to work for Python because we broke it on 2 different lines. It's not going to work, right? So how can I possibly, like when I type enter to mean like I want the string to have a new line, that means go to the next lines. Oh, a little bit of a conundrum. So how do I do that? You can do /n and then print /n means go to the next line, which is kind of neat. /t means tab, which is kind of neat, right? ASCII table. You know what? I think we should end here because this could actually we could have a little bit of fun. But it turns out each character is actually a number, by the way. And each number is also a character, kind of. We'll talk about that next time. All right, cool.